on atomic theory. All right, chapter 4. It's the first real chapter on chemistry we're going to be doing. All right, what have we been doing up till now? You might think to yourself. I mean, we haven't been doing chemistry. Well, we've been doing preliminary stuff. Last chapter was all about the math. I don't know what your class is going to be like. I graded the other ones, and the grades were pretty good. The average was a 90, and the median was a 93, which means half the class or more got an A. That's pretty good. I don't know if that's going to be your case, but my guess is it'll probably be pretty similar. But that was all preliminary stuff. So was the chapter before that, which was on scientific method and, physical versus chemical. What is chemistry? That kind of stuff. This is the first real chemistry chapter. We're going to talk about atoms and atomic structure. All right? I'm going to start off with something I don't do a lot of. Probably should do more if you're, but I don't. And that's the history of the atomic theory. Okay, a little bit of the history of the atomic theory of chapter 4. We'll get into the modern atomic theory. We'll get to the real atomic theory, what we believe to be true about atoms soon enough, probably sometime starting Wednesday. Because today, we only have a single. Tomorrow we have a double. We're going to spend some of that time doing the lab report, and some of it going over the test, and some of it watching a Bill Nye video. Okay, we like Bill Nye. He's great. And it's on atoms, of course. All right, so a little bit of history. I do a little bit of history because a lot of times you guys think you're smarter than you are. Certainly Emily does. Which is not hard to be wrong on that. But most of you do. Most of you think, oh my God, those people who lived hundreds of years ago thought the earth went around, or the sun went around the earth. The earth was the center of the solar. They were so stupid. And you probably think you're so much smarter than people who lived hundreds or even thousands of years before you. They thought there were spirits in the trees, and and thunder and lightning were the gods. Thor. Now we make movies out of Thor and other comic book characters. But still, I kind of give you this because a little bit of history lesson because you don't realize how old the atomic theory is. The first guy to come up with the word atom is a Greek word. And it comes from a guy called Democritus, who lived around, there he is. Oh my God, did you see it? Wait. Turn the light off. You got to see this. This guy's really scary. Especially when he comes at you, like out of nowhere. You ready? He's going to eat your children. Like Mike Tyson. He's like the Mike Tyson of Greece, probably. I don't know. Anyway. There he is. Look at he's a nasty guy. Look at the mouth on him. Anyway, when did he live? He's this guy that came up with the theory of atoms. When did he live? 460 to 370 BC. That's a long time ago. Somewhere around that time. Circa that time. That is one ugly dude. I do like the beard, though. He could be on Duck Dynasty with that beard. Probably not. It kind of looks like he's, it doesn't look like one of their beards. Really, this isn't important. But anyway, he was the first guy to come up with the word atom. He basically, it was more of a philosophy than a science. Back then, science wasn't what we think of as science today. It was based more on logic, conjecture, reasoning, through analogies, and through, philosophical reasoning rather than experimental reasoning. That's something that's relatively new. But the first guy to come up with the idea that all matter is made of very small particles that can't be divided into something smaller was him. And that's 2,500 years ago. It's a long time ago. You guys probably thought atoms, the atomic theory, was like Einstein's era, like maybe the 1940s or after Hiroshima, Nagasaki. But it wasn't, all right? It actually, the original theory of the atom was very, very old. So you're not quite as smart as you think. And also, another reason to show you this isn't just to show you how stupid you are. That's one good reason. You should all feel stupid around people who lived a long time ago. Because even though they may have had different knowledge than you had, they were pretty smart guys. Even just 100 years ago, people with a college education were way smarter than people who graduated college education today. Way smarter than me. I'm not talking about you. Like, I'm so much smarter than you. I'm talking about I'm so much dumber than people who graduated in the early 1900s or in the 1800s. They all had to take multiple languages. They all had to read all the major classics. They had to read Dante's Inferno in the original Italian. They had to be able to read Latin and Greek. I mean, that was just common. You had to do those things just to get a degree. You know, I mean, nowadays, you could go through your entire 4 years of college in any field pretty much and never read Shakespeare, never read any of the classics. You know how hard it is reading Shakespeare in high school. It's like very difficult because it's Old English and all that sort of stuff. Imagine having to read something in a different language. That was a difficult thing, a difficult piece. These guys are pretty smart. That's not the only reason I want to show you this. I also want to show you how we learn about things you can't see. Because you can't see an atom. Nobody here has ever seen an atom. How do we know they exist, and how do we learn about them? All right, well, let's just follow the history here. It took a long time to get any more information than just the atomic theory according to Democritus. Dalton was the next guy who really gave us some reason to believe in the atomic theory. And he lived around, oh, there he is. There's a picture of him thinking. Looks very, very intense thought there. He lived around 1803. He came up with this theory, I should say. And there are basically, and I forgot to change this. Please change this. There should be 5 statements, not 4. I forgot to change it. A little typo. Okay? Now, the funny thing about these statements, you might wonder as I go through them why this guy's famous. Why am I even mentioning him? Because let's look at the first statement. First statement says, all elements are made of atoms. Well, geez, somebody said that 2,000 years before him. Big deal. That was already a theory. That's his first statement. So he wasn't famous for that. Couldn't be. That couldn't be all he did. Number 2, atoms cannot be subdivided. Is he right about that one? Are there things smaller than atoms? Yeah. What are they made up of? What are the things that make up atoms? Protons, neutrons, electrons, sure. And those things can even be subdivided. Yeah, quarks and leptons and hadrons and there's string theory and all this other crazy stuff. All right, we're not going to go into that. We're just going to, well, protons, neutrons, electrons, we are. So he was wrong about that. This is a famous guy. Let's look at number 3. All atoms of a given element are identical. Is he right about that? Are all atoms of the same element the same? Think of carbon, for example. You ever hear of carbon-14? Carbon-14 dating? Or uranium has uranium. There's different forms of uranium. What's that word for an atom? Most atoms have these. Same atom, but different numbers of neutrons. Anybody know? Also called a fat atom. Some people call it, when you were in elementary school or middle school, you might have heard this. I know you've all heard the word before. It begins with an I. Ionic is a good guess, but it's not. What was the other one? Not ion. Begins with an I, ends with isotope.
Isotope.
Yeah! Wow, you guys are quick. Just like that. Little hints, and you get them just like that. Isotope, right. Karen's over there thinking, huh? She's looking at me like, what? Okay, he was wrong about that one too. Well, this is a little weird. He said something everybody else knew. He's wrong, and we're talking about this guy. Well, he's got 2 more things to say. Let's see what he says. Atoms of 2 or more elements combine to form compounds. Now, that's all. That is true. We kind of know that. Like, think of water. What is water made of? Hydrogen and oxygen, H2O. What's salt? NaCl. Okay. So he's right about that. And that's an interesting little, but he found out this. He really came up with this part of it in the next one, basing his stuff on experiments. He was able to actually measure how much hydrogen and oxygen combine. They always combine in the same kind of ratio. They always had a simple whole number ratio. Okay, he did experiments. And he basically realized that chemical reactions involve a rearrangement of atoms through these experiments. And that is actually why he's most famous. I'm going to put down a little statement right after all these little things that he said. And I want you to realize that the reason he's important isn't really for any one of the things he said. After all, we all believed number 1 before that. Everybody kind of thought that anyway. 2 and 3 were wrong, turns out to be wrong, proven wrong within a few decades after he came up with his. That often happens in science. I told you about that before in the scientific method. Science rarely says the same thing for any length of time because it's always being, some little part of the theory is always being proven wrong or being refined or being, perfected. It's mainly because of his experiments. The fact that he actually, for the first time, had a reason to believe these things. He had some experimental evidence. He's important because he based his theory on quantitative measurements of chemical reactions. He wasn't just making things up. He wasn't just philosophizing. He wasn't just thinking off the top of his head and saying, this is how I think things are, and I'm a pretty smart guy, so believe me. Which is to say he used the scientific method to do these things. He was able to combine gases and realize there was always a whole number ratio at the bottom of it. So there must be a single particle that can't be divided. Otherwise, you wouldn't get that ratio thing. You wouldn't get that simplest whole number ratio. I mean, he wasn't sure. He never saw an atom. But he was able to figure that out through simple or I should say, not conjecture, what's the word? Inference from that. All right? Almost like, I know it's probably hard for you to understand, but let's try to think of it this way. Let's say I had a stack of books, okay? A stack of books. And I weighed, maybe 5 stacks. You didn't know how many books were in each stack. But each one of them was a multiple of some number, was able to be divided into them. I could pretty much figure out what one of those books probably weighed, couldn't I? Right? If I had like 5 different stacks, each one, one had 100, another one had 300, another one had 500, another one had 20. And every one of those stacks, there was a number that I could divide. It was an exact number that went into those 5 stacks that I measured, or maybe 10 stacks or 20. Chances are, and assuming that number was also less than the size of the stack, chances are that probably was the weight of one of the books. That's kind of like his thinking was. All right? All right, now let's go to the next guy. We had Democritus, Dalton. All right, things kind of take off now. It took 2,000 years to get some actual proof or evidence for the atomic theory. And pretty soon, within a very short time, we're proving Dalton wrong and expanding and refining his theory, like Thompson did. This is Thompson here. Your next one to write down there? And I have a little video of what Thompson did. I actually used to have this apparatus. I used to do it for you as a demo. Over the summer one year, it broke. It came in, found it in pieces. So I've been trying to find it again, but I don't think they make them anymore because they kind of are a little dangerous. They can they strike metal. I think they can give off X-rays or something like that. And you probably shouldn't be using it anyway. Because I've been trying to find one. I haven't really found one since then. But this is the same piece of equipment I had. First of all, he worked around 1897. Now look between Democritus and Dalton, there was about 2,000 years. Between Dalton and Thompson, there's only less than 100 years. Things start picking up the pace after a while here. Let me show you what he did. Take a look here. Oh, I almost forgot. I got to pause it here. I need the sound. I think that's the right one. All right.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons.
Now let me pause it there. Now I had that exact same one. I mean, it was the same base I remember on it, that wooden base there at the bottom. And what that is a glass tube with all the air sucked out of it, a vacuum inside of it. It's almost all the air sucked out of it. Okay? You probably know light bulbs kind of make a popping sound when you break them. They have a lot of the air sucked out of them for the most part, right? That's what that is. Kind of like a light bulb when it's clear. And there's no filament in it. It has a screen in it. Okay, and that screen is phosphorescent, so if it gets struck by an energy source, it will light up. Okay, now we're going to hook up, he's going to hook up a battery, basically, a large or a high voltage source to it, and see what happens. This is what Thompson did.
And a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
Okay, so what did Thompson do? He discovered, put that light back on. He discovered negatively charged particles, and we call them electrons. And these things are smaller than atoms. We know now what they do. We know a lot about electrons now, but they're still really strange guys. We have a whole chapter devoted to them. So now, not too long after Thompson, we get Rutherford. And he discovers some stuff. This is not, I say not too long, I mean, it's within what, how many years? 10 years or so? A decade, maybe? He comes along. And he discovers something else. Let's see what he does. Again, you might want to hit that light for me.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low-mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
All right, so what did Rutherford basically discover? What did he discover? What were those alpha particles, which are positively charged, by the way, hitting and reflecting off of? What do you think? What other particles are in a nucleus that are also positively charged? Not electrons. Electrons are, what charge electrons have? They're negative. You just showed that with the crux, the tube, Thompson's thing. No, they hit what? Protons. Protons are positively charged, but not just protons, but the whole nucleus, protons and neutrons. The protons are positively charged, but it's much heavier, much more massive part of the atom. Larger part, not larger size-wise, but larger heavy-wise. So Rutherford basically discovered, well, that's just the same thing. And this is the picture, by the way, it's on your screen. He fired particles at this gold foil, and this is important to realize, guys. Most of those particles, that's not really illustrated by this diagram very well, most of those particles went right through the foil without being deflected. And only a few of them were deflected off. And that foil was very thin. You know how thin it was? It was so thin it was transparent. You could actually look through it. Gold foil, transparent. And a few of them were deflected by the nucleus, by the protons. Okay, and so he basically discovered positively charged particles in the nucleus. We call them protons. So within a couple of decades of Dalton's saying there's nothing smaller than an atom, we now have two things smaller than an atom: a proton and an electron. But there's something else you have to realize that Rutherford discovered by this. Sometimes it's not obvious. The fact that most of those particles went right through tells us that what was in its way? Was there anything in its way? No. Most of an atom is just plain old empty space. Most of an atom is just empty space. That's the other big thing that he discovered, believe it or not. So much so, and none of those pictures really illustrate this very well. Neither the one I'm going to show you in a second or the one you already saw illustrate the size of an atom in relative terms. Let me show you what I mean. That is not a representation of the size of an atom. It's not an accurate representation of the size of an atom. If this were the size of the nucleus, the atom itself would be about the size of a football field. If that were the size of the nucleus, the atom would be a football field. That's how much empty space there was for these things to go through. Okay? By no means is this representative. Like, it just has like the atom is like just twice as big or even 10 times as big. It's 99.99% at just empty space. Okay? All right, we're almost done. We have one more guy I want to talk about. I know history is not your favorite class when it comes to science. Anyway, last guy, Milligan, and again, I want to illustrate here how these things were done, how you get indirect measurements able to make conclusions without actually seeing these things. Yeah.
Why do we have this full name but not the other people?
I don't know.
I was just wondering.
Yeah, I don't know why I did that. I guess you don't need to know, Robert. Just Milligan's fault.
Okay, I was just wondering.
Yeah, that's a good point. I never thought of that. Now, again, last chance here, the last little video clip, too, of what he did. This is probably the most complicated one of the experiments. But let me first of all start it off. Turn the light on just for a second. Start it off with, turn the phone on, too. It's another example of indirect measurement. I used a second ago how you could tell that pretty much what one weight of one book was, or 1/4 if I used a stack of quarters. I could figure out what each one of them probably was, because if there was all the same multiples in each one of them, could be divided by that. Now, say I asked you to use a ruler, this ruler, to measure how thick this page is, one of these pages. How thick it is, not how wide, not how long, but how thick it is. And I had to use that ruler. Once again, I can't do it with just a ruler and that page. Unless I do what? What could I do? Yeah, I can measure the thickness of the entire book. And if I know how many, right, are in there, I know how many are in there, I can actually figure out the actual thickness using this ruler of a page. That's kind of what Milligan did. If you turn that light off again, both of them actually. All right, you'll see that in this last one. Here he comes.
In 1909, Robert Milligan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Milligan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay, so very similar again, indirect measurement. All right, he was able to, through his working around, again, 1909, we're talking just a couple of years later. Not only do we now know electrons exist, we're able to get the charge on them. And you got to realize something about electrons, people. Electrons are not what you think. It's not like, oh, well, nowadays we can look at electrons. I can put a bunch of electrons under a microscope and I can see them. That's not at all what an electron is. We have an entire chapter. It's the next chapter, by the way, I think. Or we have periodic table in between them, I forget. We have an entire chapter based on just the electron. just learning about electrons, because they're that weird. Okay? Well, just within a couple of years, Milligan is able to find the charge of an electron. Okay, you determine the charge of an electron. And he did that through the experiment you just saw here. He suspended charged oil droplets using electrodes. Okay? You don't have to understand exactly how that worked. Okay, it's not important. The key again is indirect measurement. I can't see an electron, but I can still tell his charge. I can tell he's positive or negative by using a magnet, and I can tell his actual size of the charge through this experiment. You basically determine a charge of the charge it requires to suspend a huge droplet, which has got many, many electrons on it, and then realize they're all divisible by the same number. Okay, 1.6 times 10 to the negative. But that should be, by the way, up here, guys. 10 to the negative 19th, that should be an exponent. It just didn't come out. That's not 10 minus 19, which would be negative 9, but it's not. 10 to the negative 19th. Okay?